Hi everyone, let's do chapter 10 on conic sections, polar coordinates, and polar curves. Most of these notes are handwritten, so these lectures will help to organize them. Let's get right to it. Conic sections include circles, which we know very well from before, section 0.13, ellipses, which we're now going to do, which are ovals, kind of like warp circles almost. And then later on, we're going to talk about hyperbolas and parabolas. Now, parabolas we saw back in chapter 2. We'll talk a little bit more about them in chapter 10, just a little bit. But in chapter 10, I really want you to be able to analyze ellipses very carefully. Again, ellipses are ovals, basically. Special types of ovals. All ellipses are ovals, but not all ovals are ellipses, all right? This is not an ellipse. It's too squarish. All right, let's get right to it. 10.3 on ellipses. And we're going to start with the key anatomy, notation, and mechanics for ellipses. And we'll talk about more features later on. The locus definition of an ellipse. Well, what do we mean by a locus definition? That's more of a set theory or a geometric definition of a geometric figure. So for example, what's the locus definition of a circle? Well, for a circle, you have a fixed point called the center, right? And a circle consists of all points that are equidistant from that fixed point, that distance being the radius. And you don't need x coordinates or y coordinates to talk about that. But what's the locus definition of an ellipse? Now, an ellipse does not have a single radius, as you see, all right? It does have a center. Okay, we do still have a center here, but we don't have a single radius. The points on the ellipse are various distances away from the center. Now, instead of focusing on the center, we're going to focus on two other fixed points called the foci, which is the plural of focus. Foci is the plural of focus. So we have one focus over here, f sub 1, one focus over here, f sub 2. You can use different notations. Now here's the idea. Again, for a circle, the idea was that every point on the circle had the same distance from this fixed center. Over here, it's a bit different. If you take a point on the ellipse, you can consider the sum of the distances between this point and each focus. Basically, this length here plus this length over here. And the idea is that this ellipse here consists of all points whose sum of distances from the two foci will stay constant. The sum stays constant. So for example here, a d sub 1 plus d sub 2, the point here has sum of distances from the foci, same as for this point over here. Okay, for this point P2, d sub 3 plus d sub 4, the sum in purple is equal to the sum in red. This corresponds to the way that the ellipse is constructed, and I've shown a video on this, all right? Imagine that you have two thumbtacks that we're about to attach to the ends of a taut string, okay? So you have this string here that's bent over at the ellipse, right? And the ends of the string are tied down by thumbtacks, right? Now your pen or pencil or marker pushes out on the string until it's taut. There's no slack in here, right? You move the pencil or pen around, and as you do that, you form an ellipse. This makes sense because since the string is being held taut, this sum of distances from the points on the ellipse to the two foci will stay the same because the string maintains its length. The total length of the string stays the same. All right, let's talk more about anatomy, terminology, all right, the anatomy of an ellipse. Okay. Just like for a circle, the ellipse does have a center. And the center is the intersection between the major axis over here and the minor axis over here. In a way, you can think of the major axis as the longest diameter in an ellipse, and the minor axis is the shortest diameter in an ellipse of all line segments or chords that go through the center. So you don't count things like that. Okay, so you can think of the major axis as like the longest diameter, the minor axis as like the shortest diameter, in a way. And they both have to go through the center. They intersect at the center. The two foci, F and F prime, we've discussed before. These are the two foci that helped us draw the ellipse in the first place. The two endpoints of the major axis are called vertices. An ellipse has two vertices. A parabola had one vertex. A circle had no vertices, really. A parabola has one vertex, right, over here. An ellipse has two vertices, and they are at the endpoints of the major axis. They're the 2 points on the ellipse that are furthest away from each other. Again, they're at the endpoints of the major axis. The endpoints of the minor axis don't have great names to them, but they're often good to graph with precision. Again, the minor axis extends from this point to this point. All right. Now this, by the way, this particular ellipse is called a horizontal ellipse. Later on, I'll call it an x-long ellipse in the sense that it's elongated in the horizontal or x direction. All right. Notation. So look at the center here. The distance between the center and each vertex, I'll call the vertices V and V prime. In red here, I'll call the vertices V and V prime. The prime here does not mean derivative. It's just a piece of notation. So A is the distance between the center and either vertex. B is the distance between the center and either endpoint of the minor axis. So the major axis has total length 2A. The minor axis, which I'll put in green, the minor axis has total length 2B. To be or not to be? It's 2B. Right. Now that's for a now for a horizontal ellipse, it looks like that. For a vertical ellipse, again, this is for a horizontal ellipse over here. For a vertical ellipse, it looks more like this. Okay. One moment. Okay, one moment. For a vertical ellipse, okay. Vertical ellipse or Y-long ellipse. Okay, now for a vertical ellipse, okay, the center is over here, all right? Center's over here. Major axis is vertical. So, you know, for a horizontal ellipse, the major axis is horizontal. For a vertical ellipse, the major axis is vertical. Okay, major axis is vertical. The vertices are at the endpoints of the major axis. Let's say V here and V prime over here, or vice versa. Right? The foci, by the way, would lie on the major axis, in red here and in red here. So the major axis will have 5 key points: the center, the 2 foci, and the vertices. Over here, see, we have the center, the 2 foci, and the 2 vertices. 5 key points on the major axis. So over here, we're going to have 5 key points on the major axis. This, okay. Again, the length is 2a, just like before. For the minor axis, the length is 2b, just like before. All right, but just in different orientations. Now, the major axis is longer than the minor axis. They cannot be equal because otherwise we'd have a what? We'd have a circle, right? The major axis has to be longer. So that means that A has to be bigger than B. That is, B is less than A. And they both have to be positive. So we'll assume that 0 is less than B, which in turn is less than A. In other words, A is greater than B, and both are positive. If A were to equal B, again, we'd have a circle. But a circle is not technically an ellipse. Sometimes when you're thinking about the theory and the way these shapes work, it's sometimes convenient to think of a circle as like a degenerate ellipse, but a circle is not technically considered to be an ellipse, although it's sometimes convenient to think of it as a degenerate ellipse. Okay. Now, what's C? We have A and B. What's C? C is going to be the distance between the center and either focus. So we have C over here and C over here. Remember, A is the distance between the center and either vertex. So this is going to be A over here. This is going to be A over here. This distance between the center and either vertex. You can see here C is less than A. Okay, C is going to be less than A. All right. And we know that B is less than A also. So both B and C, we know, are going to be less than A. So how do we compute C? It turns out, and I'll show you later on why this works, maybe next time, C squared equals A squared minus B squared. Look at that. Now, don't confuse this with the Pythagorean theorem. The Pythagorean theorem said C squared equals A squared plus B squared. Now, the Pythagorean theorem is involved here, but the way that the triangle is labeled, the right triangle is labeled, it goes C squared equals A squared minus B squared. I'll show you why it's a minus later on. This does make sense because remember, we just said that C was less than A, right? The distance between the center and either focus, C, is less than the distance between the center and either vertex. In other words, the foci are closer to the center than the vertices are. C is less than A, which makes sense that here, right? It makes sense that A squared is going to be less than C squared, okay? Because C squared is going to be A squared minus this positive value here. Okay. So this reflects the fact that C is less than A, the fact that that's a minus sign. All right. So again, C is the distance between the center and either focus. That's the case for a horizontal ellipse or a vertical ellipse. In this class, we're not going to do 45-degree ellipses, although you do see those in Calculus 2, Math 151, rotating conic sections. In this class, we might rotate them like 90 degrees or 180 degrees, but not 45 degrees, not in our class. Next up, we're going to talk about standard forms for the equations of ellipses. Next time.